Righto, well, there's no one here. It's nice and quiet. Let's have a look at 7.4 magnetic forces on a moving charge. Now, just to make things confusing, when we're looking at forces on a moving charge, so we're not looking at the magnetic field around a wire, current carrying wire, or the magnetic field around a solenoid, we're looking now at magnetic forces on a moving charge. So there's two different ways that charge could be moving. I'll move in here and you can see it. Forces on a charged particle or forces on a current carrying wire. And for both of those, you use a left-hand rule. It's down the bottom here. And I was trying to think of a way for you to remember it. So I came up with this, you'll love this. Thumb. So thumb is for force. B, which is your index finger, is for boogers, magnetic field. So B for boogers. And I in the center is for I don't care what you think. Right? So F for thumb. So that's the force. B for boogers on your index finger, magnetic field. And I for I don't give a whatever for your center finger. Right? So that's the way it goes. Force, magnetic field, current. I is current. In case you couldn't remember that one. Righto. Goes through there. Cathode ray tubes were very important. They're not so important now, but they used to be the thing that was used to make any kind of a screen work. And if you see a really old television, you'll see that they're not thin like today's TVs. They're quite deep. And the old ones from the 50s and 60s were quite really deep, massive things. And that was because they had these cathode ray tubes in them. And what they did was they determined the electrons would be fired. This was an evacuated tube. Electrons would be fired in, and the magnetic field would then change the trajectory of the electrons, and that would hit a phosphorescent screen here, and that's what you looked at. That's what created the image. So the magnetic field was used to manipulate the electrons and light up the screen. So they were in any old 50s, 60s, maybe even 70s to the beginning of the 80s type TVs or any sort of electrical equipment that had a screen in it. Okay, so we've got two different things to look at. We've got charged particles moving in a field, a magnetic field, or we've got charged particles, which is electrons, moving through a wire, current carrying wire. So here's our little formula for this. Would be if you were firing charges into a magnetic field, like you would be to produce an image with your cathode rays, or it's also used in analysis of different materials. They like atoms. If you want to find out what kind of atoms are in something, they get them all excited, fire them into a magnetic field and measure where they land, because that has something to do with their mass, and they can work out what size the particles were and what elements were in them and whatever. So that's in spectrographs. So here we have, this is the force on a charged particle. So magnetic field is force divided by the charge of the particle, and the velocity of the particle comes into it as well. And that gets rearranged to F equals QVB. Now that's at 90 degrees to the field. 90 degrees is important. 90 degrees gives you the maximum force. So by 90 degrees, what they're talking about is something like this, where the magnetic field would be running up the page and the charge has been fired in at 90 degrees to the magnetic field. This one here is at an angle. Remember there was a unit a little while ago about the angle of magnetic field lines. So the angle is measured here. Magnetic field lines, here's the angle to the field. That is not going to produce the same amount of force as this would. It's a sine relationship. So if it's at right angles to the field, sine 90 is not 0, it's 1. So that gives you a maximum. Sine of any other angle is going to be a decimal, so that's going to make the force smaller. Right, normally in the questions, unless it's specified, it's being fired in at a right angle. So most questions it'll be fired in at a right angle unless it tells you a particular angle. So then these examples are just straightforward as can be. You've got the size of the charge, you've got the velocity of the charge, magnetic field strength, and you've got the angle, and it's just a really simple formula. Force is QVB sine theta, and 90 degrees and 60 degrees. So just back to this formula, some things to point out then. Force is going to be, is that clear? Yep. Force is going to be directly proportional to the size of the charge. So the bigger the charge, the bigger the force. The faster that charge is going, the more force it will experience. And the bigger the magnetic field, the bigger the force. So that makes sense. And you're just going to use that. We're just going to use that left-hand rule. So you're going to have to become a contortionist. What was it? Force is your thumb. B for the magnetic field. I for, now that I said current before, so that's on a wire. The thing that's the third variable, if you're just looking at a charged particle, is its velocity, so that, or its direction of motion. So this I in the center is also the velocity. So I don't know, if you want to try and remember that, you would put your finger up quickly. I don't know, something like that. So if we've got direction of motion, magnetic field, force. So in this question, not that it asks you, you've got magnetic field, direction of motion. So you twist your hand around. So the direction of motion is across the page. The magnetic field is up the page. So that particle would actually move this way out of the page towards us in that magnetic field. Well, I'm going to do something similar then with force on a current carrying wire. This is important again for motors and generators. This is how they work, magnetic field with a loop of wire in it. And the formula is similar. There's a derivation there. It comes down to force is magnetic field by current by the length of the wire, and sine theta, which is the angle that it makes. Again, 90 degrees is going to give us the maximum. So they've got a diagram here that shows you then. So if we have got, you've got to use your left hand. So of course I'm going to have to contort myself a bit. Hang on, left hand. So magnetic field is going straight across the page. The current is going up the page. And so the force is up out of the page. They've tried to draw a 3D drawing on a flat page there. So the force is going to be out of the page. Magnetic field is across. The current is up the page. So that leaves you with your thumb going straight up. That's the direction of the force on a current carrying wire. Right, then these equations are really straightforward as well. So in one question it says that the wire makes an angle of 55 degrees. So you've just got to put 55 in for the sine theta. You've got the magnetic field. You've got the current. You've got the length of wire in meters. And that will give you your answer. So what does it say? Into the page. Oh, I'd have to twist my hand right round to show you that. But have a go at it. See what happens. What's that last one? You look kind of strange in an exam when you're doing this, but you just have to put up with it. So the magnetic field is into the page. The current, yep, this one's easy to do. Magnetic field is into the page. That's your booger finger, into the page. I, don't give a, is going down the page. So that means that across to the right is the force on the wire. So that one. This one requires too much twisting. I'm not going to try and do it while I'm filming. So that's that, I think. Then it comes over here and looks at the use of a couple of these applications. So one is a loudspeaker, and you've got a solenoid here in it. Right, that's going to be producing the vibration. And then that produces a sound wave. Simple DC motor, we've got a current in it. The reason they put a loop like this is so that the current is changing direction compared to the magnetic field. So that way you get a force up on one side and a force down on the other. And so you get a turning motion. They also have this contraption here, which is used, if you follow it round, you'll find as it comes up, there's no force when it's at 90 degrees. So it's just got its own momentum bringing it round. But then when it comes around this side, apart from the fact that this would all get twisted up as it spun around, the direction of the force would change because the direction of the current will change as it comes up and around, and you'd get a flipping. So they have this thing called a split ring, which makes sure that the current keeps it moving in a circular motion. Jordan can probably tell you more about that than me. All right, then we're up to Check Your Learning. I'll have a look through that and do a couple of those for you.